So I'm presenting on heat pumps, like everyone else, but I truly believe this is a highly underutilized technology relative to the efficiency opportunity. I want to thank Neil Elliott and Ed Ryder of ACEEE who've brought heat pump technology into the whole discussion at ACEEE and its partners with how to decarbonize US industry. So starting with the fundamentals, I think everybody on the call here understands the thermodynamics here, but it's worth to spend a second here with heat pumps, we're moving heat up and they follow the same Carnot efficiency laws as heat engines do, except we're moving heat up, right? And so the higher the heat pump lift, the lower the COP. And the type of energy used to drive the heat pump will dictate, it could be electricity, prime heat, waste heat will dictate the heat pump economics. We'll talk about that in a second. So there's many different opportunities in industry. There's heat sources listed here, heat sinks. And as Tony Buzza mentioned, the challenge here is how to effectively integrate and link up these sources and sinks with each other. There is some history at the U.S. Department of Energy from 1985 to 1995. There was a research program that I managed, and most of the focus was on heat-activated heat pumps. And as at the end of that research program, which ended in 1995, there was a international project through the International Energy Agency called Global Environmental Benefits of Industrial Heat Pumps. There was a US market study done, and I've listed the 8 key processes that found the best heat pump opportunity. If big picture, if you look at that study, the study found 2 to 5% improvement, which is not totally impressive, but realize it was with fairly low natural gas prices in 1995. And the table I show here compares those 1995 natural gas and electricity prices corrected to 2019 dollars to 2019 industrial energy prices. Interestingly, natural gas has gone down by 60%, electricity's gone down by 10%, and most importantly, as it relates to heat pumps, the electricity to natural gas price ratio has gone up by 50%. So on the surface, this is not kind of a good news story for heat pumps. That's going to make things harder, but that's in the context of looking at electric-driven heat pumps. So we'll talk about that in a little bit in terms of heat-activated heat pumps in a second. So many people think of heat pumps with industry is mainly the corollary to residential commercial, which is true. There are those vapor compression systems, but the most commonly applied heat pumps in industry so far are not even called heat pumps. They're called mechanical vapor recompressors or steam ejectors. There's hundreds of these in food processing, paper, chemicals. And then absorption systems are less commonly used. I just want to spend a second on pinch technology. I think one of our colleagues and speakers talked about pinch technology, but the important point is this has been around for 35 years. It's a kind of a best practice of how to integrate heat with industrial processes, but it's also a way to place the heat pump in the right part of the process. You do that by identifying the pinch point, and what you want to do is to place your heat pump so it's extracting heat from below the pinch point and delivering it above. That US study I talked about in 1995, that study was done with reviewing over 100 industrial pinch process studies and data, and any future study that we do on industrial heat pumping should do the same thing. We talked about barriers. Of course, energy price is a big one, and also the last one here that most of the equipment suppliers are not in the US, they're in the European Union and Japan. So it would be good to build the domestic market for heat pumps. Let's look at one example, economics with mechanical vapor compression. Here I'm taking steam at 100 degrees C, at atmospheric pressure, and we're varying the heat pump lift. And you notice once we get above 40 degrees C, we start to get over 5-year payback. The other thing, as mentioned with the other speakers, is we're limited currently at about 160 degrees C with current working fluids. Now, so what do we do about that? Well, one of the questions we were asked is, what are the major technology opportunities we're not pursuing and researching? And I feel there's not hardly anything being done on heat-activated heat pumps. And these come in two types. Type 1 would be taking higher temperature heat and then lifting heat from the source to an intermediate temperature. More interestingly are type 2, which are also called heat transformers. These are essentially entirely waste heat driven, where usually half the heat is discharged to the ambient and the other half of the heat is boosted up. So this presents a very interesting solution to get around that issue of higher electricity prices relative to the natural gas, which the electric-driven heat pumps face. So let's go through one example. I'll do this real quick. But if you look at a 1 megawatt system, I'm assuming $1,500 per kW. That's a critical metric here, is the cost of the heat pump. And if you look at current natural gas prices, which are fairly low relative to the rest of the world, you end up getting a 10-year payback on the heat transformer. So maybe that's not encouraging, but if we go to the next slide, first of all, that $1,500 per kW is for a pilot unit. It's at smaller scale. If we're able to improve the heat pump technology here, the heat transformer technology, and reduce that cost by heat exchanger innovations, material innovations, raise the scale of the heat pump to above 5 megawatts. And if natural gas prices are going to be higher than they currently are, which there's probably a pretty good chance, we can start to get down to 2, 3, 4, 5-year payback region here. So, and another specific example is a technology called Q-pinch, is being developed in Europe and marketed to the process industries. This technology is not quite absorption, but it works off a reversible chemical reaction of phosphoric acid to diphosphoric acid and water. And what's really interesting about this is it can go up to 220 degrees C and it can lift up to 100 degrees. So if something like this could work, if you could get the cost down of this unit to say in the $1,000 per kW range, then you're going to open up an immense amount of opportunity for the heat pumping industry. So in summary, critical research opportunities are, my recommendation is we develop both type 1 and type 2 heat activated heat pump cycles. They need to be demonstrated to have good material durability. They need to show that they can have good operability and reliability within actual industrial settings and processes to prove out the economics. And the working fluids need to be safe and environmentally benign. I provided some research targets. That cost target is key. And so in summary, I think there's reason to be optimistic about high temperature heat pumps. I see a sea change in industry where those companies that are serious about decarbonizing. They're willing to look at technologies that are going to make a significant impact on their energy efficiency and carbon footprint. And they would look at something, say, up to 5-year payback, whereas before they'd only look at 1 or 2 year payback. I think the R&D is justified in high temperature heat pumps, especially in the heat activated area. With modest increases in natural gas price, I think we'll see these things to be very economic. And it would be good to increase the domestic market of the companies that supply these types of heat pumps. And then finally, technology is not the only answer. I think whatever we do on the technology side needs to be married with good energy policy and incentives, such as tax credits for high temperature heat pumps. Thank you.